Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, my dear students. I want to welcome you to yet another session of TV learning. And today I'm going to be working with and learning with students of Senior 2. My name is Teacher JB. Your physics teacher. And today we are still looking at Unit 5. And in Unit 5, if you remember, we are talking about measurement of liquid pressure using a manometer. And so before we start, I want you to look at our lesson title, our unit, and then our learning objectives. And so I want you to move to our projector screen there and see what we have. And so for today's lesson, we are going to be looking at measuring hydrostatic pressure using a manometer. And also we shall look at an aneroid barometer. And we shall also look at factors that influence the difference in depth of a liquid that is in a manometer. So those are the basic things that we are going to look at during this lesson. And by the end of this lesson, every one of you must be able to describe how hydrostatic pressure is measured using a manometer. We are going to look at that, so you should be able to describe. We should also be able to give the differences and similarities between a mercury barometer and an aneroid barometer. And today we are lucky enough, we shall have a look at an aneroid barometer. Mercury barometer, remember we have been learning about it very many times, so you know how it looks like. We shall just give the differences between those. And then lastly, we should be able to explain the factors which affect the difference in the levels of liquid that is in a manometer for the same pressure of air or liquid which is being measured. So those are our lesson objectives for today. Okay? For your references, as always, you can use the Physics for Rwanda Secondary Schools Learners Book 2. I hope you have it. You can even get it on the REB website. And it is book 2, of course, Learner's Book by Longhorn Publishers. And you can look at page 92, and some content is found on page 101, 102, and 103. But of course, you can read wider than that. Okay? So, measuring the liquid pressure using a manometer. And so to begin with, we shall look at one video. The video we shall watch today will not perform the experiment here as we have always been doing. We will be able to discover how a Thistol funnel, like a filter funnel that you use in the laboratory, covered with a thin rubber skin, like a balloon skin, can be used to measure the pressure at any point inside the liquid. So that's what the video is about. Okay, so let's be attentive and watch the video. Now, in the video, we are going to have a YouTube. Do you remember a YouTube? We have been using it before. If you remember our previous lessons, this is not something new to us. So you have a YouTube with a certain liquid inside, and this is a meter rule to help us measure distances, okay? And this, of course, is a retort stand that you know very well. This is a large beaker, and inside the large beaker you have a rubber tubing, flexible, okay, with a Thistol funnel. This is a Thistol funnel, which is inverted, upside down, and this is the stretched rubber skin we are talking about, very thin, a thin skin of rubber. And it is placed inside the liquid whose density we want to measure. So, where is the manometer in this arrangement? The manometer is this. This is the manometer, okay? All these other apparatus are to help us measure the pressure, the hydrostatic pressure inside this liquid. Of course, it is going to be at this point in the liquid. So that is how our experimental setup look like. And if you want, you can still do this in your laboratory when you go back to school. Okay. So this is the video. I just want you to watch it very well. Look at what is done. So in this video, as you can see, we have a manometer. And this manometer is used to measure the liquid pressure, just like I described to you. So in the beginning, the fiscal funnel you can see is outside. You have a scale. You see, there's a liquid. You can see the levels of the liquids are the same. That means the pressure here is the same as the pressure on the other side. And this is A, and that is end B. Of course, I told you there is an elastic skin of rubber which is put at the end of the fiscal funnel. Okay? Should find that very comfortable to understand. So if you remember what we said before, what should come next? Think about it. What should come next after this? We are going to dip the fiscal funnel into this bucket, the beaker of water. And if you do that, there's a pressure being exerted on the fiscal funnel by the liquid. And the liquid is going to force, you can see, this air inside to be compressed. So this level goes down in A, and in B, the level goes up. And remember here, what are we interested in? We are interested in getting the difference here, the difference between the levels of the liquids in limb A and limb B. And if we get that, then that will give us the pressure difference. The height difference, which will give us the pressure difference, and we can use the pressure difference also to find, you know, the pressure of the liquid that was being measured by the manometer. So I'm going to take you right here. If this sketch that we saw on the video this is just the sketch. Assume this is the liquid. And remember what this one is. This is the fiscal funnel, right? And we're using this to measure the liquid pressure, the hydrostatic pressure within this liquid at that point. So what we said was, in the beginning, the level of liquid here was the same. But when you put it here, you put the fiscal funnel here, the pressure being exerted by the liquid will force the air inside to be compressed. So this level will go down, and the other one will go up. So this is the liquid that we have in the manometer. And we say this is limb A, and this is limb B. I hope you remember that. So what are we interested in? We are interested in measuring the height, the difference in the heights of the two liquid surfaces. So you have this and that. So using your meter rule, like we saw in the diagram, you are able to measure the distance from this height, this liquid surface, up to the lower liquid surface in limb A. So if we measure this, let me call it H. So if we find that H is measured to be equal to 200 millimeters. Imagine H is 200 millimeters. Then the next question will be, what liquid are we using in this manometer? If your liquid happens to be mercury, then we shall say this H changes into a pressure. And the pressure will then be 200 millimeters of what? Of mercury. Remember, we said millimeters of mercury is also a unit of pressure. So in this case, the pressure difference here is 200 millimeters of mercury. Again, if you ask yourself, what pressure is acting here? The pressure which is acting here is atmospheric pressure. I like to abbreviate it as PATM. That is atmospheric pressure. Again, what pressure is pushing down here? This is the pressure of the gas. I want to call it P gas. So gas pressure and atmospheric pressure are not the same. Gas pressure is overpowering atmospheric pressure. This is more. But remember, this pressure of the gas is being produced by the liquid. So this is also equal to the liquid pressure at this point here. Okay? And so if I want to get the pressure of the liquid or pressure of the gas, remember they are going to be the same. Pressure of the liquid at this point. So we are going to have, because it is more than atmospheric pressure, it is going to be equal to H then plus atmospheric pressure. In this case, our H is 200 millimeters of mercury, and atmospheric pressure, do you remember the value? Yes, it is a constant at sea level, which is 760 millimeters of mercury. So when you add those two, what do we find? 760 plus 200, our answer is going to be, okay? Our answer is going to be 960 millimeters of mercury. And so this 960 millimeters of mercury is the hydrostatic pressure within this liquid at this point. So if we push the thistle funnel down, what do we expect? This level of mercury will go down and the other one will go up, meaning that the pressure will be increasing with depth. And that is a principle that we had looked at before. In a liquid, pressure increases with depth. So I want to assume that that summarizes the first objective that we had. We wanted to see how to describe measurement of hydrostatic pressure using a manometer, and that is what we have done. All right. Now, when you look at this difference in height, difference in the level of liquid, you can see this and that. That is the difference we are talking about. There are some factors that determine how big or how small that difference is. If you're using two manometers, but you are trying to measure the same pressure. One of them is the pressure difference, the difference in heights depends on the liquid density. Look at these two manometers. You can see the thickness of this, the diameter of this tube is almost the same as the diameter of this tube, right? But now the liquids are different. This is a liquid with a high density, like mercury, and this is a liquid with a low what? A low density, like water. If you're measuring the same pressure, let's say gas pressure, this is gas A, and it is the same gas A, same volume, every other thing is the same, even temperature. Do you think you will produce the same difference in height? No. You will have a bigger difference in height for a smaller what? For a liquid with a smaller density. And you are going to have a smaller height for a liquid with a high density. Okay? That is something that we had looked at the concepts concerning it before. So the difference in height depends on liquid density. Okay, we want to look at another factor. Look at another factor. For the same liquid, that is the manometric liquid, this one, same. You can see the colors are the same. Unlike the other one, the colors were different. But here the colors are the same. So for the same liquid, the difference in height does not depend on the what? The diameter of the tube. As you can see, this tube has a smaller diameter, but this one has a bigger what? Diameter. For the same gas A, you can see, the pressure of gas A is going to be revealed to us by looking at the difference in height. But when you look at this difference in height, this one, we are calling it delta Z. It is the same as the difference in height there. Same. Because we have the same liquids, we have the same gas. What is the difference here? The difference here is in the diameter of the what? Of the tubes. So it means if I have two manometers, one is having a smaller diameter, the other one has a bigger diameter, don't get worried. You will get the same difference in height, as long as you are measuring pressure of the same gas under the same circumstance. I hope you get that. This is a smaller diameter, and this one is a bigger diameter, but the height difference in them is the same. Okay? Let's look at the next one. If you have same gas pressure in A, again, the same barometric liquid or manometric liquid, but you have got different tube lengths. You see, the liquid here is the same as the liquid there. What is the difference here? Is length of the manometer. Do you see that this is a shorter manometer? Yes, maybe as short as me. And then this is a longer manometer, maybe as long as Goliath, very tall. So there are two. The only difference is length. So what are we saying? Same pressures, same diameters, same manometric liquids. What will happen to the difference in height if we are measuring the same temperature, same pressure? It will be the same, just like you can see here. For as long as you have enough liquid here which can almost fill up the manometer. Okay? Then the next one will be comparing aneroid and mercury barometers. We want to compare those two. Remember, mercury barometer is this. There's a long test tube inserted inside a petri dish, and there's mercury inside. We have looked at that already. So this is mercury barometer. This one is strange to us, right? I hope you are listening to that word for the first time, maybe. Aneroid barometer. So what I've done in this diagram, I've broken this into half so that you see the parts inside. And today we are lucky to have an aneroid barometer. You see this? This is an aneroid barometer. It may not look exactly the same as that, but it is an aneroid barometer. I also have another one, which is this. If you look at this very well, you are going to see the word aneroid. Aneroid. Aneroid means without liquid. So it means this is a barometer which does not use any liquid. Mercury barometer uses a liquid. Aneroid barometer does not use any liquid. So this is how it looks like. Don't you think it resembles this? They're almost the same. Okay? Aneroid barometer. So, as I told you, I have got sort of a cross-section through an aneroid barometer. You can see, like this part here, you have got this, and so many other parts. This is a scale. And so that diagram is right here. I hope you can see it. This diagram is very similar to what you have there. So this is a partially evacuated metal box. So it is a metal box. Partially evacuated means you have removed some air from inside it. And then this is a spring with some pivots to allow movements at joints. And this is a chain which is connected to a pointer. This one is called a pointer, and that is a scale. The scale is what you have there. This pointer is this. I think you are seeing the connection. These chains here, you are seeing this part here. This is actually this one. You see? The corrugated, evacuated box is this one. You see? It is hollow inside. They just removed some air, which is this one. So that is how aneroid barometer looks like. Does it have a liquid inside? No. So right here, I just got something that can help you to understand how aneroid barometer looks like. This is not found in an aneroid barometer, okay? But can help us to understand how aneroid barometer looks like. So you take this as the corrugated, evacuated metal box. This one. Take it like this one, okay? Or this. So what then happens is, when the atmospheric pressure goes down, the pressure outside the box is very low. What then happens is this metal box will try to become bigger. And as it tries to become bigger, it will make those parts like the chains and the springs to move. If the atmospheric pressure increases, okay, outside there's a lot of pressure, it will try to squeeze the box. And the squeezing of the box makes it to contract and will cause movement. And the movement created can be measured through the deflection of the pointer. Okay, so just observe this and see, right? You can see the size of this balloon right now. If I apply pressure on this metal box, remember this is our metal box, I just want you to observe what will happen to this balloon, okay? Okay, ready to go? Okay, I'm going to apply pressure on the metal box. Do you see what is happening to the size of the balloon? Is it becoming bigger? To me, it is becoming bigger. If I remove the pressure, the balloon goes back, becomes small. If I apply a lot of pressure, the balloon becomes bigger. So it means the balloon is having some movement, okay? And that movement of the balloon will cause the chains also to do what? To move. And so the pointer will begin to deflect. And the magnitude, the amount of deflection here can be recorded as the atmospheric pressure. And that is what we have here in aneroid barometer. Does it have a liquid inside? No, there's no liquid inside. So that is aneroid barometer. Okay, let's go ahead. Now, we now want to look at differences between, and similarities also, between mercury barometer and aneroid barometer. Okay, they are very easy for us to see. I will move quickly. One, mercury barometer is expensive because it has mercury, so it's more expensive than aneroid. With mercury barometer also, it is very bulky, it is big, because it goes up to about 3 feet. It contains a liquid which can easily spill. The mercury can easily pour out, and that is a disadvantage. But, okay. And that is a disadvantage. But now when you look at aneroid barometer, you see it is compact and solid. You see, solid. I can turn it upside down without any fear of the liquid pouring. So it's comfortable. And it is small. I could even put it in my pocket, in my small bag. But mercury barometer is quite long. It comes up to around this size. So it is hard to transport. And because it is made of glass, it is very brittle. It can easily break. So those are some of the differences and similarities between aneroid barometer and mercury barometer. And so as we conclude our lesson, I will leave you with some assignment to do. But before we go to the assignment, I want us to look at the main items, the main concepts we have learned in this lesson. What are the main concepts we have learned in this lesson? One, we were able to discover today, using the other video that we looked at, that you can actually use a manometer like this to measure the liquid pressure, which we call hydrostatic. Static means liquid which is not moving. So we call it hydrostatic pressure using a manometer. So if I want to know the pressure, I just need to look at the difference in height. So we have been able to look at that. Knowing atmospheric pressure, then we can get the pressure being produced by this gas, which is of course coming from the liquid, then we can calculate the pressure of the liquid at that point. As we take this down, then the pressure increases and the height also increases. We have also been able to look at an aneroid barometer. Physically, we have seen how it looks like. We have looked at the internal structure of an aneroid barometer, and we have also looked at the main parts in an aneroid barometer. That's why we are able to say this is an evacuated metal box with less air inside but more air outside. So as the pressure reduces, the box can become smaller, or bigger. Okay, as the pressure changes, the box can either become smaller or bigger. And as the box changes its size, it means any other metals, chains, and pointers and so on, which are connected to the metal box can also move. And their movement is reflected by the scale. And so the amount of movement, the amount of deflection will give us the pressure at that point. That's something what we have been able to look at. And then finally, we are able to look at the differences between mercury barometer and aneroid barometer. And so to end our lesson, I'll leave you with this homework to do. Quite very easy. One, define the term hydrostatic pressure. So what is hydrostatic pressure? Two, draw a well-labeled diagram of a mercury barometer. That's something that we had looked at before. So can you draw that diagram? Then, a mercury manometer is used to measure the pressure inside a column of liquid X. Okay? So in that manometer, you have got mercury. The difference in height in the mercury column is 20 millimeters of mercury, just like we saw on the other diagram. The difference is 20. What is the hydrostatic pressure of X at that depth? If the atmospheric pressure is 760 millimeters of mercury. Okay? Should be able to be comfortable with that. Then lastly, give any three advantages of using aneroid barometer compared to mercury barometer. Good. So once again, I want to thank you students for being attentive and being active in your own ways during this lesson. I want to pray and believe that you got some concepts from this lesson. How I wish that you continue watching programs, academic programs, and then you can join us for the next session. Have a good time till we meet next time. Bye-bye.